All right, are we ready? Hello, everyone. Welcome to Math Night 2024. I appreciate. I'm Frank Casano. I'm the math department chair here at MA. Yeah. Thank you so much for coming, both in person. I know we have some people joining virtually as well. This is a crazy night that, to be honest with you, as math teachers get together today in the last couple of weeks, we don't think is really going to end up happening. And sure enough, we walk in today and it's happening and our kids are ready. It is so cool because there's no grade attached to this. The students want to do this. We have a plethora of auditions and unfortunately we can only take so many. So I really appreciate everybody who did audition and then everybody obviously who is going to be presenting tonight. It's wonderful. A little history of Math Night. Rich Clear started Math Night even before Kevin, which is a long time ago, right? Rich is not here.
He should be here around 7.
So Rich is going to be here at 7, so we'll make sure to give him, little shout outs later on as well. But we're going to keep rolling it every year. Like I said, it happens. It happens, and it's always amazing. But it doesn't happen with the math department and my team. So a big shout out to Kevin, Jamie, Rachel, Taylor, Anya, Molly, Ian, Josh, and John. I didn't leave anybody out, right? This is a crazy, hectic time for us. We're doing placement exams. We are guiding students in their petitions for honors or not honors next year. And we potentially have somebody who just graduated and earned her master's degree in education the other day. So without further ado, we're gonna start it off. So I'm gonna ask Ian to come on up to start our presentations or introduce our first presenters.
Yeah, I'm not presenting either. Hi, everybody. So I have the pleasure of introducing our first presenters. We're going to have Charlie and Victor come up. Charlie, this year, you're in multivariable, correct? And Victor, you're taking linear algebra, if I'm not mistaken. Awesome. Good for you guys. What they're going to talk about today is something that we've explored in our geometry classes in the last handful of years, and it's going to be gerrymandering. So they're going to hit on some stuff that some of you might be familiar with, which is awesome, but they're going to expand a little bit deeper and get to some places and ask some questions that we might not have thought of in the past. There is going to be an interactive portion of this. So do me a favor, have your phones ready. Don't have them out. Not away, just a little away. And so make sure you're ready to be able to interact because there's going to be a survey at one point. So without further ado, come on up, gentlemen.
Technology. Here at Marin Academy, we love democracy. There's just something so appealing about our system of government, a system where every citizen has a vote, and every vote counts equally.
Or does it? And we're not even talking about the issues posed by low voter turnout or fraud, but something far more fundamental. Let's discuss the mathematics of gerrymandering.
So the term gerrymandering just describes the process of drawing electoral district boundaries unfairly. It was first done by this man, Elbridge Gerry, in an attempt to win the 1812 Massachusetts elections, where his Essex South district was caricatured as a mythological salamander. Gerry's salamander, or the gerrymander for short. And ever since then, gerrymandering has been literally everywhere, and it's been done by both Democrats and Republicans in equal measure.
Now, this is a good time to clarify that gerrymandering isn't actually illegal. Something like bipartisan gerrymandering, which favors the incumbents, which has no change no matter the political party, is protected by the Equal Protections Clause of the 14th Amendment. What is illegal, however, is racial gerrymandering, which is gerrymandering to limit the voting power of a specific race, which is a protected minority group. For the rest of the presentation, since we're only talking about the problem of illegal racist gerrymandering, we'll simplify by using these two terms interchangeably. So how does gerrymandering work? There are two main methods, packing and cracking. In packing, we cram the opposing party's supporters into a small handful of districts, where they will win each district by a much larger margin than they actually need. Whereas in cracking, we spread the opponent across a bunch of districts where they won't muster enough votes to win a single district. So let's take this example, which has 60% purple voters and 40% gray voters. Now, if we crack gray across 3 districts like so, purple wins 3-0. However, if we pack purple into 1 district like so, then the majority purple faction actually loses 2-1.
Okay, so this racist gerrymandering exists, but it's illegal. So what's the problem? Well, what's critical to understand is that gerrymandering, this insanely powerful tool for electoral abuse, is really hard to detect in advance by hand. So to hopefully show this, here I have 4 maps of North Carolina's congressional districts every 4 years. Exactly 2 of these 4 maps have been gerrymandered. Can you tell which ones? So when you've made up your minds, please either use the QR code in the middle or go to slido.com and type in the code and tell us, again, which 2 maps of the 4 you think are gerrymandered. You might have to zoom in with your camera. There should be a QR code that pops up, a link. And let us know if you're having difficulties. Are we finishing up? No? Okay.
Okay. Oh, yeah, that's right.
All right, looks like we're about ready. So let's see how you did. Here are your votes. We think it's the first 2, maybe a little bit of the 3rd and the 4th. So in the 2008 election, even though the map looks a little bit wonky with all these elongated districts everywhere, it was actually pretty fair. There was no racial gerrymandering at play. So we expected the vote to be even because of the general vote, and it was. But then what happened is that the Republican Party won control of the North Carolina Assembly for the first time in over 100 years, and they wanted to keep it that way. So for the 2012 elections, what they did is they packed Democratic voters into these 3 districts, and they won the other 10, despite the even popular vote. So then in 2016, the US Supreme Court said, no, 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 this violates the Voting Rights Act. And they forced Republicans to redraw the districts. So the 2016 elections used this new map, which looked far cleaner. See, it's got nice big chunks, sorry, none of those big salamanders flying around. And it looks far cleaner, and it's also the map that you guys thought was not gerrymandered. However, it turns out that this map was still gerrymandered, and it gave the same outcome, a 10-3 win for the Republicans. Then finally, the courts took it into their own hands, and they drew their own non-gerrymandered map for the 2020 elections, which immediately returned Democrats 2 seats in a more reasonable 8-5 election.
What do we learn from North Carolina? Gerrymandering is everywhere. It's devastating to our democracy, and it's practically impossible to detect by hand. So we have mathematics to the rescue. First, the simplest way to detect gerrymandering is to analyze the compactness of a district. In this example, even though districts A and B have similar areas, District A has a much smaller perimeter, which means it is more compact than District B. We can visualize this difference using a method called the rubber band test. Here, we can clearly see that the smallest circle around District A has a similar area to District A, while the smallest circle around District B has a much greater area than District B. So now let's take a look at some formulas we can use to actually measure compactness. If you've taken geometry at MA, you might remember some of these. So first we have the skew. We find the skew by surrounding the district with the smallest possible rectangle, finding the dimensions of this rectangle, and then calculating the following formula, width divided by length. Next, we can find the isoperimetric measure of a district. And we do this by finding the area and perimeter of the district, and then calculating this formula, 16 times the area divided by the perimeter squared. We can also find something called the square reich of a district. We do this by surrounding the district with the smallest possible square, and then finding the area of the district and the area of the square surrounding it, and then we calculate area of the district divided by area of the square. Now, for all 3 of these ratios, the closer the result is to 1, the more compact the district is, and the closer the result is to 0, the more skewed it is. And of course, if we want to determine an even more comprehensive representation of a district's compactness, we can simply choose to use all three of these formulas and compare the results. But remember, what we're doing right now is measuring compactness, not necessarily measuring gerrymandering. Although compactness is a good place to start, just because a district isn't compact, that doesn't necessarily mean that a racial gerrymander has taken place. There's a lot of legitimate reasons why a district might not be compact. For example, the district's border might follow a natural boundary or a county line. Some districts are also designed to protect minority voters' rights. So considering all these possibilities, a lack of compactness can be a sign of potential gerrymandering, but we need more information to confidently say that gerrymandering has occurred. So moving on to an even more reliable method, we have the efficiency gap. What the efficiency gap is essentially the difference between the percentage of wasted votes for each party in a region. So what's a wasted vote? A vote is considered wasted if it's in a losing district or if it exceeds the 50% threshold to win a district. In this example, Green has 45 wasted votes in this one packed district that they won, while Pink only has 5 wasted votes in this district. On the other hand, Green has 45 wasted votes in each of the cracked districts they lost, while Pink, again, only has 5 wasted votes in each of these districts. Running the numbers, we find that 78% of Green's votes are wasted, while only 12% of Pink's votes are wasted. So the efficiency gap works out to be 66%, which indicates a clear bias toward Pink. Now, if the Supreme Court were to establish an efficiency gap threshold, we could develop a measurable way to detect gerrymandering within our legal system. However, we still cannot say for sure whether this gerrymandering was intentionally biased. So this forces us to develop another method that is even more precise.
And that brings us to our third method of detecting gerrymandering, the best one we currently have, and it involves something called Markov chain Monte Carlo. So to understand it, we can start with just some basic probability. Imagine we have this tiny state with just 16 voters, some of which are Democrats and some are Republicans. This microstate needs to be divided into 4 equally sized districts. So here are all 22 possible ways to do this. Again, this is every single possible districting of this 4x4 grid. So now we can look at the outcome associated with each of these 22 possible districtings. For example, if we draw districts like this first one, we can see that the first district will be a tie. The second district will be won by the Republicans. The third one will also be a tie. And the fourth one will also be a tie, giving Republicans a total of 2.5 votes. And I can hopefully see, I hope you can see how this corresponds to this districting right here. And then if you keep repeating this process for every single one of the 22 districtings, you get this graph. And you can see that in a randomly chosen district, Republicans win on average 2.7 votes. We can also see from this graph that only one of the 22 districtings gives Republicans only 2 votes. And that's this district right there. So if this districting just so happened to be chosen, that would give you pretty good evidence that there was Democratic gerrymandering. But sadly, the real world is a little bit more complicated than this 4x4 grid. So as you've seen, the 4x4 example has 22 possible districtings. Then the 5x5 one would have 515. The 6x6 one has 55,000. The 7x7 case has 20 million. And then the 8x8 case took someone with a really good computer over 30 hours just to calculate. The 9x9 number of districtings is so large, we don't even know how to calculate it yet. Meanwhile, in the real world, North Carolina has a population of over 10 million, split across 5,000 voting precincts. So in the best case scenario, we could only represent that with like a 70x70 graph, which we just think about how impossibly big that number gets. So our previous method just doesn't work here, but it's absolutely the right idea. And here is exactly where the Markov chain Monte Carlo comes in. So what if instead of having to sample literally every single one of the gazillion possible districtings, you could just pick out a small representative sample? It's like how polls don't ask every single American. You just ask a small representative subset. So here's what the Markov chain Monte Carlo algorithm does. You begin with just some randomly selected districting. And then, one step at a time, you begin to shuffle those districts around in a predetermined way. Now, this is a 7x7 graph. And as we just discussed, it has 20 million possible districtings. This animation is not going to get you all 20 million, but what it can do is give us a representative sample of that 20 million. And while the actual proof that this is a properly representative sample is undergraduate thesis material, literally, it can be shown that the Markov chain Monte Carlo algorithm does generate a graph that converges to the ideal distribution we discussed before.
What we find really cool about this is you can go out and actually find so many examples of this exact process being used right now in real life. For example, there's this Duke senior thesis that used a type of Markov chain Monte Carlo called stratified sampling to look at those two gerrymandered North Carolina maps that you all voted on earlier in this presentation. They generated a sample of 38,000 possible maps and analyzed the resulting graph, and they convincingly showed that both of these maps were gerrymandered.
But this algorithm does more than just let us look into the past. There's also this Markov chain Monte Carlo generated sample of 3 million maps made on a literal supercomputer used as evidence in a recent 2020 gerrymandering court case. And as you can see, it's pretty convincing. The probability of the actual Ohio map being randomly chosen is pretty much 0. And then best of all of this is stuff that you can just go and do yourself. So there's this wonderful GitHub repository called JerryChain that has all the code and instructions you need to get started implementing this on your own.
Okay, so here we have a 3D model that helps us to visualize the probability of different districts actually occurring in real life. Essentially, we can think of each point in space on this model as a different possibility for a specific districting, with the average likelihood of that model actually being created represented on the z-axis. On the x and y-axes, we can choose to represent any combination of variables that influence the district, such as population density and racial makeup. Now, building these multidimensional models also connects our statistics problem to the area of multivariable calculus quite nicely.
But just this math isn't enough. We didn't actually tell you the full story of North Carolina. Remember that Supreme Court ruling labeling the 2016 district as a racially discriminatory gerrymander and drawing new, fairer boundaries for the 2020 elections? Well, after the North Carolina Supreme Court flipped Republican in that same 2020 election, it reversed the previous decision, all but legalizing racial gerrymandering in North Carolina. This was then taken to the US Supreme Court, and I'm not going to lie, I spent like half an hour trying to understand the 65-page Supreme Court ruling. It was a bit too much for me. But I think that they just said, we're not sure, because apparently that's a thing the Supreme Court can do. Here's their exact language. Quote, "We decline to address whether the North Carolina Supreme Court strayed beyond the limits." So as things stand, gerrymandering is pretty much de facto legal in North Carolina.
Thanks to modern advances in mathematics, we finally have the tools to end gerrymandering once and for all. This is a crucial step moving forward in protecting our democracy, but we still have work to do outside of mathematics. We must ensure these tools are accepted into our legal system and that they're used to protect voters' rights in future elections. The methods we've discussed today are great in theory, but if we don't put them into practice soon, we cannot create real, lasting change. Thank you.
Thank you.
I think it's just on, right, Jamie?
Oh, perfect. Okay.
Hey, Anya.
Hi.
All right. Our next set of presenters are two wonderful sophomores,
Juniors.
juniors. Thank you. Had old age, right? As Frank likes to point out. I'll stop talking. You go, Dom.
And their names are Drayson and Kaylin. We absolutely loved working with these two over the past few months, and they're going to present on a cool probability paradox as well as some real world implications of it. So let's give it up for Drayson and Kaylin.
All right. My name is Kalen Blodgett.
I'm Drayson Jaffe, and this is our presentation on the friendship paradox.
All right, so we're going to start with an activity. Can I get 5 volunteers? All right, let's start over here. I'm just gonna have you pick 2 strings out of the bag without looking. Right. All right, we got a green string, and then we've got 5 different colors of strings in this bag, and we got a red here. All right, you can replace those. Anybody else? Okay. 5 different colors of strings in this bag, 4 of each string, and we're just randomly selecting the strings. All right, yellow, and then 1 more. And that's a white string.
Okay.
All right, 3 more. Let's do 1 for each of you. No looking. Yellow and red. All right. Good. Okay. Let's... Yellow and and white. All right. And we need 1 last volunteer. I'll go to the other side. All right, red. And another red. All right. Okay. All right. So, why did we do this? We're going to calculate the average of the lengths of these strings. Okay.
So we collected a sample of the strings, and now we have, and each string color has a designated length to it. So now we're going to calculate the average. So we had red is 25. We had 1, 2, 3, 4 red. So 4 times 25. Then we had 1 green, which is 15. So that's plus 15. And we had 3 yellows, which are 20. And then 2 whites, which are 10 plus 10. So that is 115, 195 over 10 equals an average of 19.5 inches. So the average length of string in that bag should be 19.5 inches.
And the actual average, 15 inches. So, does anybody know why this might be the case? Yeah.
Small sample size.
Small sample size?
That's one possible reason.
Yeah.
Yes. That is exactly right. You are much more likely to pull a longer string out of the bag because it occupies much more space. When you reach your hand into the bag, you are far more likely to grab the longer string than the smaller string because the smaller string is just way too small for you to grab.
So this activity was an example of something called sampling bias. And sampling bias simply states that certain members of a group are going to have a higher probability of being selected compared to other members in the group. In our situation, there were strings with larger lengths, therefore they had a higher probability of being selected.
All right, so now we have created another example. So let's say we have a person named Frank. No relation, no relation. That's not you. Then we have Rachel, Ian, and Taylor. This is related, not you. They are connected. So Frank is friends with Ian, Taylor, and Rachel. And they are all friends with our amazing head of school, Travis. And then there's Anya, who is friends with Ian and Travis. Josh is friends with Ian and Travis as well. Then Jamie is friends with Josh, Travis, Ian, and Taylor.
And this is now what we would call a social network. And so we're now going to figure out what we can do with this and show an interesting relationship in it. So we've taken each of the values here, that are the number of friends of each person in this network. As we've calculated, the average to be 4, with Anya having the lowest at 2. Sorry, Anya. And Travis has the highest, of course, at 7.
All right. So now we're going to calculate the average number of friends of friends. So how do we calculate this? So let's say we have Frank, and Frank has 4 friends. Frank's friends, first of all, Ian has 5, Travis has 7, Taylor has 4, and Rachel also has 4. So on average, Frank's friends have 5 friends.
So if we continue calculating these for the remaining people in this social network, we'll find, for the most part, it seems like people have less friends than their friends have, which you can only notice with Travis and Ian being the most popular people in this friend group. They're the most popular, so they don't have friends who are as popular as them. But when we calculate this average here, we find that the average here is 4.8, greater than 4, which means that the average person in this friend group has less friends, is less popular than their friends.
So this is called the friendship paradox. We got there.
So this was something that was theorized and proved in 1991 by a psychologist by the name of Scott L. Feld. He wrote a paper about it called Why Your Friends Have More Friends Than You Do. And you can read that paper if you want to. It dives a lot deeper into the mathematics behind this. But these are all examples of something called inspection paradoxes, which come from a branch of probability theory called renewal theory. And we're going to give you a couple more examples of its inspection paradoxes here to hopefully help you observe the pattern between them.
So a first example is the class size paradox. This is relevant for admissions to high school and colleges because one of the things that they're going to tell you is their average class size at the school. So let's say a college says they have an average class size of 18 people. They are sort of lying to you. You are much more likely to be in a class of larger than 18 people simply because more people are in that class. So if the average class is 18 students, the average person is going to have the average person's class is going to have an average of students in it of way more than 18 because they are much more likely to be in that class.
All right, another example of this you can find in public transportation. And this could be applied for trains, buses, any sort of thing like that. The company that's running this business is going to report an average wait time between the arrivals of buses or trains. And you will find that the average experience of a passenger is going to be higher than the average reported by the company. And this is just simply, again, because these longer wait times are going to be experienced by more passengers just because they're longer.
And then we have a bunch of real-world applications as well. So one thing that we can do is identify influential nodes in social networks or our popular people. And then one way that we can apply this is through the spread of disease and pandemics, such as COVID. If we can identify who the popular people are, for example, we have a manager in an office who is going to talk with their employees very often and connect to them more often. This person is the very popular person that is connecting with a lot of people. So a lot of disease can be spread through them to a lot of other people. So then by identifying that central node and that important node, we can slow the spread of a disease.
And another way we can use this data is to magnify social contagion, which means that we can identify social trends and predict them before they might actually happen in a social network. For example, if we took a random sample of 50 MA students, and we asked them, who do you think your top 5 most popular people are at MA? We can take the most popular answers from those people, and now we have a much more efficient way to predict social trends that we might see happening at this social network. It's a lot more efficient than just sampling based on random samples. So yeah, it's very helpful. Yeah, thank you.
All right. I think we have one more presentation, then we'll take a short break. 2 more presentations. Never mind. But our next presenter is Nate. And Nate and I first got to interact back in Nate's 9th grade year. Nate's a senior in honors geometry. And one of the things that I talk about a lot in that class back in the day and still is that it's less about the content that we learn and more that we try to get better at learning. And when Nate started sharing what he's going to share with you all, I realized how important that was, because it was something that was really, really abstract. And it was really fun to see Nate's excitement for it and Nate pulling in all these different tools he had to get to the bottom of a really complicated problem and to get ready to share it with you all today. So I'm fired up for Nate. I know Nate's fired up to share with y'all. So give it up for Nate.
Hi guys, I'm Nate, and I'm going to talk to you about this really cool thing that I found last year. It's called the Autodidactic Universe, and I'd love to share. So for some context too, I don't understand this fully, so I'm just going to share kind of what I can see. But if you want, I would love to send it to you, and you can look at it yourself too. So with that being said, yeah. So I'd love to start by talking about how the universe, kind of like as a concept and as a thing, is like this really, really like particular and like interesting thing, at least from our perspective. So in that way, the fundamental building blocks of our universe, so matter, dark energy, are all kind of balanced for what we can see in like just this right way, and like just this right like kind of orientation, so that galaxies and stars can exist. If it wasn't, the entire universe would look probably radically different, maybe a massive empty void, and we would have no way of knowing. Similarly, the weak nuclear force is then just strong enough to make the right amount of hydrogen for life so that we can be here. If it wasn't, there would probably be much less hydrogen, and the universe could be a massive empty void, cut off. As well as that, we can see that the cosmic microwave background, which shows us like the matter distribution, like the very beginning, we can see that it was just uneven enough to give us like the densities that we need to exist for galaxies to all kind of come together. If it wasn't, it could be empty void again, which would be really sad. So it's all this like really, really great coincidence that everything kind of worked out this way, maybe. And we don't really know why, but we have like all these really, really cool theories. You've probably heard of the Big Bang, which we think is probably right now. But there are all these other ones that we found, but we would love to know, are there more? And specifically, like how we can kind of like differentiate them and find like what we're trying to look at. So in this way, we have this problem with every current theory at the moment, all the ones on the last slide, which is that none of them have found this like compelling reason or an argument for why all these like coincidences that I laid out and why everything kind of like happened in like just this perfect way, so that galaxies and us and everything else can exist in the way that we do. So what if instead we theorized based on that assumption that all these coincidences aren't actually just like this like amazing like perfect like lottery system, and we just happen to win it. So I mean, in other words, we spent all this time trying to discover like what all these laws are and like how it all worked, but really haven't like questioned why and like how all of it kind of came to happen. So what if instead the universe doesn't have any predetermined physical laws? There's no explanation for the weak nuclear force with its like crazy constant that ensures that everything kind of works in the magical perfect way, because it isn't actually constant. What if instead physics has somehow evolved in this like Darwinian, like evolutionary, really, really cool way that explains how the laws of the universe kind of works together in like just the right way for us to exist? Isn't that cool? So I present the Autodidactic Universe. It's another paper, and it's by all these people. It's really great. It was published a few years ago. Massive paper. It's like 80 pages long. That's why I said at the start. I haven't read all of it. I've read enough to get like a little bit to share with you guys, but I am by no means like an expert in it. Notably, really, really coolly, it's the last paper co-authored by that guy, Lee Smolin, who's really, really cool. He's this like renowned theoretical physicist. He's made all these amazing contributions to quantum gravity theory, particularly in loop quantum gravity. which is what we're trying to see could be like this kind of like unifying theory to bring together general relativity and quantum theory and give us something that combines them. Really interestingly, kind of this presentation, just like keep in your mind, he advocates that loop quantum gravity and string theory, which are like the two kind of like dueling primary approaches to this explanation, are both just different aspects of the same underlying thing. So just like keep that in your mind, because that's really interesting. And then this is his last kind of like swing for the fences, like big like paper and big like kind of go out with a bang thing to kind of just like give the whole scientific community and to give us something to chew on. A la Stephen Wolfram, who did the same thing. So where do we start with that? After reading this, I kind of found their big kind of hypothesis, which is that are machine learning systems useful as models for the formulation of fundamental universe theories? There's a lot there, but I think it serves as like a good kind of roadmap for what I'm trying to go into here, which is trying to relate machine learning systems, a la like ChatGPT and AI and all that really, really cool stuff that's been in the news, and then getting that all the way over into these like fundamental, like crazy universe theories that we think could be like our clue to seeing like how it all started and like what happened there. So again, the big idea, machine learning and quantum gauge theory, which I'll get into and explain. But broadly, kind of what I just said, we're just trying to like look at the similarities between these two separate fields and see if there's any like similarity overlap, which is not like a complete equality, because it probably isn't. But just trying to see if there's any overlap and like how that could work. And that brings us into that idea of a learning universe, which is really cool. So I'd love to start first with this concept of invariance, which is this really, really cool concept in machine learning programming. And all it really means, even though it sounds really fancy and really cool, is that the same thing by definition can be represented in different ways. So in this like scenario, you have just a rectangle in motion that is being represented in different ways on this like grid system, which then can be, which then is still the exact same thing in definition and in function, but then is just shown in different ways. Similarly, this gets a lot more complicated with something like this for training a machine learning algorithm to try and recognize what a statue is. If you have all these different like ways of like transforming it through translation, through rotation and viewpoint, size, and even like illumination. So, as I just said, invariance plays this really crucial role in machine learning systems. It prevents algorithm overfitting. So it encourages this like learning of like really, really generalizable models that I can apply to all instances of this statue, not just like that one. It can apply to every single one here, and is often seen as the end goal of many algorithms. But how do we apply this concept and start kind of like bridging the gap all the way over to like universe theories and stuff? So that's where I bring it into calculus. It's okay if you guys like don't remember a lot, but I'd love to kind of like ease us in. So given any function equals a constant, we could then say, using kind of like this new special language of invariance, that its derivative or its slope is then just invariant to that parameter c, to any point that we put in there, or any value. Because the slope of it is just always going to be 0. Shown here, no matter if it's 2, if it's 4, if it's 5, its slope is always going to be 0 because it's just a constant. Similarly, in the same way, we just scale up a little bit. Given that function again, just a b of x plus c, which should just be a 1, but whatever. That derivative we could then be invariant to the parameter c, meaning that no matter what value you choose for c, its slope is always going to be 1 or b. In the same way, and kind of doing the exact same thing, you could have its c be 2, 4, or 5, and it's still going to be the same function in practice when you're looking at the derivative. So that's all well and good. But then how can we bring that even further out? Which is where I go even further. So given a function, which is a little farther, given a function with an even degree, you could then say that its derivative would then always be an odd degree, which is kind of out there. But in this context, you can see that with the parabola, its derivative is always just going to be a straight line. So then you could say that the property of its like the property of its degree of the derivative could then be invariant to whatever this number is, as long as it's even. So in the same way with this, as a quadratic function, its derivative is always going to be a cubic function with the derivative of with a derivative degree of 3. So that's kind of a lot. It's okay if you didn't get that like fully. But where can we go from here? And that's where we take it into physics, with most famously, the most famous instance of this concept of invariance in physics, which is that the speed of light is the same in every frame of reference, aka no matter how fast the train is moving. In this scenario, the beam of light right here will always be c. So as you can see here, because of the conservation of momentum, the model didn't show exactly what it needed to do, so I put it in 300. The arrow would then be fired if it's being fired from the same at the same velocity, but from a moving train, it would then be 300, and would then be faster than if you were just standing on the ground, as opposed to if it was just a beam of light going from the train or from a stationary person. It's going to have the exact same acceleration. So again, as another example, kind of more grounded, given that temperature in a room is homogeneous, you could say that it is then invariant to an observer's position. So if you just said that the temperature in this room is 75 degrees, no matter where you measure it, it's always going to be 75 degrees. But there's also more, and this is where it gets kind of zooming out again, which is with gauge symmetry. So in the context of kind of even deeper physics, when describing an electromagnetic field, you can describe its vector potential in a bunch of different ways with, importantly, arbitrary values. For the context of this point, you don't need to know what that or that really is. All you need to know is that it doesn't matter which way you choose to describe it, because the field itself and its function and what you're trying to describe will always stay the same. AKA, you can change how you describe something, but it is still the same thing in function and in practice when you're trying to do stuff with it. Sound familiar? And then again, this is just one example, but this concept of gauge symmetry, using vector potentials and anything else, is this core principle in our understanding of quantum physics, general relativity, and almost all modern physics. So it's really intrinsically tied into all those universe theories that I talked about at the start. But again, that should sound familiar. I think I did it too fast.
You may need to
You
touch
might
the
have
screen.
touched it.
Oh, you touched the screen.
There you go.
Cool. Because in this way, if you kind of followed that, you could then say that both invariance in machine learning and gauge symmetry share the same underlying concept, i.e. that process of describing things in multiple ways while still generalizing to the same definition in the end. So just in this context with the statue, you could describe it in all these different ways, and it would still be a statue in its function to a machine. You could describe the vector potential of this electromagnetic field in all these different ways, using any value you really wanted, and it would still mean the same thing in function and in practice. Now, does this inherently mean that the universe is a machine learning algorithm? Probably not, but there's still definitely merit, and it is really cool to explore this, as shown in the paper, which again goes really high level for a sec. This is from the conclusion, just kind of showing what you could do. So just imagine you could use these correspondences to construct like a quark computer, which computes using the spins and isospins of quarks and gluons as qubits, which is just this crazy, I don't even know what that means. But it's really, really cool. And we could figure it out. And we wouldn't be here if we didn't go on this whole journey, which is really cool in itself. And I think that makes this cool in itself just to look at. So kind of going all the way back to the start, with all these crazy theories that we have, I'd like to kind of go and put this all in context. So again, kind of rip straight from the paper. what he says. Roughly speaking, we are faced with a singular stark choice. Either that there are no rational reasons for any of these choices and any of these values or anything, and the universe might have been very different, but there will never be a reason that, or why it took the path that we observe it on. Or there's at least one rational explanation, in which case we are obligated to find it as scientists and as humans and everything. To ask that question is to suppose that, for instance, everything and the constants could have been different, but not randomly so. A scientific explanation would suggest that their values are set as a result of a dynamical process, which means it can be modeled analogously to all other time-dependent processes we're familiar with, i.e. machine learning systems. That's a really, really big stretch, even in itself. But it does still kind of prove the point that even if this is a really, really far reach, and there's not a lot of evidence to back this already, it is still cool in itself to look at. And that's where I'm going to leave it with this one last quote, the last quote of the paper, which is probably very familiar in a lot of scientific papers. But that the results themselves here are tiny baby steps towards these hypotheses to be further explored in future work. Thank you.
All right, thank you, Nate. Hi, everyone. My name is Josh, and I had the pleasure of working with our next presenters who are going to straddle intermission for you. They're going to start with a little card trick before intermission, a little food for thought, and then after intermission, if they're feeling generous, they're going to show you where math makes the magic happen. So please help me welcome Yukeen and Gordon. Here you go.
Oh, cool.
You can clip those. There's little clips.
Oh, yeah. Okay. Hold on. I'm not sure we call it like this because this is not working. Oh, you got it.
What if I just hold this?
Oh, I figured it out.
Okay, wait.
All right.
Here we go.
It might be. All right, y'all.
Wait.
I went to the theater and borrowed this top hat.
Wait.
So, yeah. See, that wasn't even math. Unfortunately, I don't know any jokes. That would be great. That'd be great. Well, while we wait, we're gonna have we've got a card trick we're gonna do. Duh. But we're gonna have some people come up and do the trick with us because just to prove to you all, there is absolutely no sleight of hand, trickery, tomfoolery, none of it. This is it's pure magic. And so can we get 4 volunteers to come up here? All right. I see 3 people raising their hands, so oh, never mind. All right. Luca, Tati, Ray, you in the back, I don't know your name. Asa.
Wait, we can get more people also. If,
All right.
if more people want to do it. Here, wait.
Honestly, anyone else? We have a whole deck, so.
Yeah. If anyone else wants to come down.
If anybody wants some cards. Yeah.
Okay.
So
Gordon's gonna give.
Yeah.
Well,
Pick a card, any card, and then do that 3 more times. Because you need 4.
Yeah, 4 cards.
Yeah. Just pick 4 cards.
I'm taking the blue one.
I trust that you can do that, Asa.
I'm not trying to count.
You ruined everything.
Yeah, I know. I always do
Why does it matter, Tati?
Okay. Here,
right.
if some of you guys could stand over here, so I'm
Yeah.
not so lonely.
Yeah.
Anyways, we don't need the screen.
To do it along with them and also for the purposes of the rest of you guys, I'm going to use some slightly larger cards.
Yeah. Okay, so each of you guys have 4 cards in your hands, and it doesn't matter what cards they are, you can look at them. But after you familiarize yourself with your cards, you're gonna want to put them face down in a stack, just one on top of the other, like that. And
Like
then
this.
hold them in the middle, and you're gonna want to
Rip
you're gonna
straight down the
want to
middle.
rip them in half.
Yep.
Yeah, yeah.
Yeah.
Like
rip
down the
them,
middle.
Lisa.
Like
Fully.
this way,
Like this. Straight.
Like down
Yes.
the middle.
Straight down in half like that.
Okay.
Y'all got it. All right.
So Tati, you ripped them the wrong way.
Now here we go.
You didn't follow Gordon. Bro.
Come on. I did it for you.
Anyways,
All right. It's fine. Whatever.
it's okay. It doesn't matter.
This actually should still work, even though you've ripped them the wrong
Okay.
way. You're just gonna.
Now,
No, you do not.
okay. Now you're gonna want to put one
One stack
on top of the
straight
other.
on top of the other.
Yeah, just like that. Okay, perfect. And you're gonna think of how many letters are in your name. So, for example,
I'm Gordon. That's G.
so for every letter in your name, you're gonna want to put the top card at the bottom.
Yeah. So G, O, R, D, O, N. So you guys can all do that for however many letters you have in your name.
Okay.
Great. Yeah.
Now take the top 3 cards.
Sorry.
Take the top 3 cards and
1, 2,
put them
3.
anywhere in the middle of your deck.
Yep. Just stick them right in there. Anywhere you want.
And you're in the middle. Make sure it's in the middle.
just-
Okay.
The requirement for the middle being not the top, not the bottom.
Okay. Now.
You know, sometimes you gotta spell it out.
Okay. Here's the important part. Listen very carefully. Okay. Don't mess this up. Take the top card and save it for later. Keep it in a safe place.
Safe place. For me, that's my hat.
Okay. Lovely. Okay, now, if you guys are a dog person, take 1 card off the top. If you're a cat person, take 2. And if you're both or neither or something else, you can take 3.
I had a pet frog when I was a kid. His name was Edward. I loved him so much. And for years, I said I was an amphibian person, partly because I hated the conflict between dogs and cats. I thought it was silly, but also because I love my pet frog, Edward.
Okay.
We got these 3 for me.
Take those 3.
I'm gonna go in the middle. It's not that deep.
take those 3 and put them in the middle of the deck again. In the middle. Yeah,
Yep,
anywhere in the
anywhere
middle.
in the middle.
In any order, doesn't matter. Just in the middle.
And now we got our deck.
Okay. Now, you're going to do some self-reflecting. If you were born... It's
So
okay.
we just
it's-
did some
it's-
self-reflecting.
If you were
This is
born
the
on
easy
an
part.
odd day, take 1 card off the top. If you were born on an even day, take 2.
I was born on the 12th, so I'm gonna take 2 off the top.
And on the count of 3, we're going to toss them all up into the air. Well, the 2 cards you're holding, or the 1.
The 2 you've just taken.
Okay, so 1, 2, 3, go.
Sorry. I was worried that was gonna happen.
Okay. Wait, Ray, what day is it? What day of the week? Tuesday, thank you. Okay,
true.
so for every letter in Tuesday, we're gonna take the card from the top of the deck and put it at the bottom. So T, U, E, S, D, A, Y. Okay, perfect. Now, some game I used to play as a child is where you would take. Why are you guys laughing at me?
It's true. This is not a. This is not a Yukine thing. This is.
Thank you. Okay.
Thanks for clarifying.
You take a flower and you pluck off petals saying like, oh, he loves me not. So we're gonna do that with this deck of cards to see if it's meant to be.
It's gotta
So
be meant to be.
take the top card, put it at the bottom. Take the next one, throw it away. And take the top card, put it at the bottom. Take the next one, throw it away. Take the top card, put it at the bottom. Take the next one, throw it away. Take the top card, put it at the bottom. Take the next one, throw it away. And some of you guys may be left with 2 cards, so you're gonna do it one more time with me. So if you're left with 1, don't do it. Take the top card, put it at the bottom. Take the next card, throw it away. And now, take the card that you saved from later.
For all of you
I mean
guys
earlier.
wondering.
And for the grand reveal, you can put them
Hold on.
together. And show the audience, and they can all be the same card.
There it works. United once more. There you have it, folks.
Anyways, I think it's intermission now, so you guys can
And,
think about it, I guess.
Yeah, a great magician never reveals their secrets, and so we are going to leave you guys with intermission to think about this yourselves. And while you guys do that, we are going to clean up this mess. Thanks, y'all.
Sure.
Okay, everybody, we're gonna take a little intermission. We'll come back here and we'll start. We'll hear the big reveal at 7:40. All good? Let's do it.
Oh.
That's amazing.
No, it's incredible. Thank you.
Okay.
All right.
Yeah, we're back.
Yeah, very back. And you know how before intermission, I told you that a great magician never reveals their secrets? Well, I got great news for y'all. Yukine and I are not great magicians.
Yeah, we're not. We'll get there.
We are mathematicians. And so we will be explaining to you how this trick works in great detail. In fact, all of the detail. Yeah,
So everyone starts off with 4 cards. There's nothing special about them.
it's just 4 cards.
And then once you rip them in half and you place them one stack on top of the other, this actually means here. We're gonna tape them onto the board so you guys can see.
Here we go.
Okay, as you can see, each card, each half of pair is exactly 3 cards away from its other half. So the queen has 3 cards in between the other half of the queen. And this means no matter how many letters are in your name, for example, my name has 5 letters.
And
So
my
if I
name has
rotate
6.
this 5 times, it doesn't matter because, hold on, 1, 2, wait, here, I'll push up. 1, 2, 3, 4, 5. It doesn't matter at all because look, the queen still has 3 cards in between.
Whoa, hold on. I forgot to push one. Where got that? It's fine.
Gordon, I believe in you.
Yeah. This is actually. That was harder than the trick was. All right. Well, you know, as you can see, our queen, 1, 2, 3, queen pattern stays the same. So when we ask you to take 1, 2, oh man, 3 cards off the top and put them in the middle, doesn't matter where in the middle, because what we're really doing is taking the card that was 3rd from last, is now in the front, and you'll notice its pair is all the way at the back. And so then when we ask you to take the top card and save it for later, put it up here, all we really got to do now is follow the queen in the back of the deck.
Okay, so the cats and dogs question was just a bit of misdirection because like 1 card, 2 card, 3 cards, it doesn't matter where you put them because you're not putting them at the bottom of the deck, so it's not going to change the location of the only card that we care about.
So then when we ask you to take cards for your birthday, same goes, because you're taking 2 cards or 1 card, in my case 2, out of the deck. But this has a more serious consequence than the cats or dogs question, because now we've lost 2 cards. We have 2 less cards in our total rotation, which is going to be quite important later. You'll see.
And for me, I was born on the 31st, so it's an odd day, so I'm only taking 1. And that means I have 1 more card than Gordon. So the next step is when I asked, I don't know who I asked, but I asked someone what day of the week it was, and Tuesday. And, you know, it is Tuesday, but a very special trait about Tuesday, the word Tuesday, is that it has 7 letters in it. And that means we're going to rotate the deck 7 times. And since I have 6 cards, that means rotating the deck 6 cards is just going to have it back to the start. And then I rotate it 1 more to get 7. So just for the sake of time and ease, I'm just going to rotate it once.
Since I've got 5, mine is going to be a net rotation of 2 after going just once through.
And now you may see that me and Gordon's decks look different because the card I care about is in the 5th position and the card he cares about
is
in
in the
the
3rd.
But at our next step, when we start doing the petal plucking, take the top card, put it at the back, take the next, we throw it away. And suddenly my deck has shifted to look exactly like Gordon's, with the queen
Queen
in
in
the 3rd.
position 3. And so then when we continue doing the petal plucking, the queen in 3rd position is always going to be what you end up with. We know because we saw it happen like 6 times. But the question really that we're here to talk about is not that it happens, but why it happens. And so I'm gonna show it to you real quick. We go take 1, put it at the bottom, and take another, throw it away. Now our queen is in position 1, which means again it'll go to the bottom, and the 9 will get thrown away. And then queen's in position 3, same thing happens. To the bottom, thrown away. Queen is back in position 1, goes to the bottom, survives 1 more round. The 3 gets thrown away, and we're left with just the queen, right? Of course, it's easy to, do it and show you, but the real question is like, what is the actual math? Because it is math night, and we do have to explain why. Well, this is actually something that we can tell by drawing out a nice little diagram, because what we're really doing is eliminating every other position, and it changes every time. So we have 1, 2, 3, 4, 5. We keep 1, and then we eliminate 2. We keep 3, and we eliminate 4. We keep 5, and then we eliminate 1. And then we keep 3, and then we eliminate 5, and then we're left with 3. And this exact same pattern can be done for if you had 1, 2, 3, 4, 5, 6 cards. You'd keep 1, cut 2, keep 3, cut 4, keep 5, cut 6, keep 1, cut 3, keep 5, cut 1, and you're left with the 5th card in
Which is,
and you'll notice that's
which is,
exactly
yeah, where my
where
queen
Yukin's
was.
5th card was before we did this 1 cycle through. So we let her do it 1 cycle through, for the sake of clarity, but you can see that regardless of which number you start with, there's always going to be a determinable 1 that gets selected at the end. And if you've taken MA geometry, or for a few of you taught MA geometry in the past couple years, you might recognize this as the queen's pattern, hence the queen. So because we have, basically, it's just a pattern that we learn where in the chosen card gets brought up by every odd number until you hit a power of 2, and then it resets, and it does that forever, which is pretty cool. But that's actually what's going on here in this card trick. And I don't exactly know how to, conclude this with a flourish because the card trick is over. But here you go. Yeah, that's it. Go. I'll erase the board now. Wait, the magnets work really well.
Oh, yeah, sure.
Yeah, let's call Luca.
How does this work? Clip it on to your clothing somewhere.
So what struck us when Tilly and Luca auditioned was their charisma, curiosity, and humor. You're in for a real treat with this dynamic duo. Without further ado, presenting Paradoxical Shapes, I give you senior Luca and freshman Tilly.
Okay. Hi, I'm Tilly,
Hi, I'm Luca.
and we are going to be talking about paradoxical shapes. And if you don't know exactly what that means, we will get to that. So,
Do the clicker. Clicker.
oh yeah. Thank you for being on top of that. So this is a little bit about what we're going to talk about. And if these look like things that you have never heard of, don't worry, because we'll get to that. And yeah, we hope that you'll just learn some cool stuff. So you should have been given a piece of paper and a piece of tape. If you didn't get one, just look on with your partner. And we are going to make our very own Mobius strips, which is one of the things that we talked about today. And to take a page from Gordon's book, I'm going to make my own,
the other
but
one?
bigger. What?
Do the other one.
Oh, they're back there. Okay. Don't worry. So what you're going to do, take out your piece of paper, make sure it's flat, then bring the pieces of paper together, take one side, only one, and flip it 180 degrees and no more. And then take your piece of tape and tape that together. And you now have your very own Mobius strip, and it should look a little something like this. Hold them up. Yeah? Good? Mobius strip. Okay, cool.
Great.
So, yeah, go ahead. Okay, so these are cool. And they're often used as a representation of infinity because they're an endless loop. And that brings us to kind of the cool part about them, which is that even though you've just folded a three-dimensional shape with two sides, your strip of paper, you now have a one-sided structure, and which makes it sound two-dimensional, and even so can only exist in our three-dimensional world. And an ant walking along this Mobius strip would be able to cover every surface of it without ever crossing over an edge. And to show this, you can trace your own finger over the side, and you'll notice that you can cover every area of it without ever crossing it. What? No, go back. Oh. Okay, so now you haven't been given scissors because we don't have that many scissors, but you might be able to, but if we were to take this and cut it down the middle, what do we think might happen? Oh, sorry. We should have said this.
If you know what happens, don't say what happens.
Yeah, if you've seen a Mobius strip before, don't say it. So, yeah, we're going to reveal it, but for now, just tell someone next to you what you think might happen.
Is there two ways to get back here? Okay.
Okay.
I don't know, Nate. What happens?
All right. So.
Victor, don't get ahead of yourself, buddy. You're not that guy.
Okay. Stop talking to your neighbor. We'll tell you. So your intuition should tell you that, like most things, when you cut it in half, you should have two of them. But what actually happens is something a little bit like this. which is another Mobius strip that's also one-sided, but with 2 twists, as you can see. And if we were to cut this in half again, we would get, Luca,
Yeah.
you to smooth this. Oh,
Oh,
oh
no.
no. Oh no, oh no. Okay. Well, I promise that this isn't fake and that this is actually what would happen. Oh no. Okay.
Yeah. That's something
Is
like that.
2 double twist Mobius strips interlocking with one another.
Only by
Pretty cool.
twisting once. Yeah.
Yes. So, yes. And this Mobius strip it exists in our 3-dimensional world, but in 4 dimensions, it's something called a Klein bottle. But to understand that, we first need to talk about what dimensions are. So 2 dimensions is what you're seeing on your screen now, on this screen now. Things that are surface level with length and width, I don't know, with no depth. And in our 3D world, they're not physical and they can't be held.
So for example, a square is 2-dimensional because you can travel in 2 directions along it. And a drawing of a tree is 2-dimensional because it's not actually a tree. So 3 dimensions is our world. We can travel in 3 directions. We can travel length, width, and height. So that would be a physical object like this clicker that can be held. So you can see up, down, left, and right. And so a 3-dimensional equivalent of a square is a cube. And a 3-dimensional equivalent of a drawing of a tree is a tree.
And now before we get into 4th dimensions, we're going to talk about 1 dimension, not because it's relevant, but just because it's cool. And that is either length or width, but not both. Similar to 2 dimensions, there is no depth. And in a 1-dimensional world, you would only be able to see one direction. So a square would just be a line, vertical or horizontal. You can, we have a little line if you don't know what a line looks like.
Yep.
And a drawing of a tree, because it can only have 1 dimension, would just be a line.
So you can think of them as cross sections of each other. So the drawing of a tree is a cross section of a tree. The line is a cross section of a drawing of a tree. So here we go.
And now on to 4 dimensions, because we're living in a 3-dimensional world, 4 dimensions doesn't exist as we know it. Someone living in a 2-dimensional world can't even fathom what a 3-dimensional world looks like. They don't know that up and down even exists. So theorists, including Albert Einstein, if you've heard of him, theorized that the 4th dimension, in addition to length, width, and height, is time. So instead of seeing up, down, left, and right, you could see up, down, left, right, past, present, and future. Yeah. So this is what we think, or this is what a 4-dimensional cube or square would look like. And it looks a little weird here because we're trying to show you 4 dimensions on our 2-dimensional screen.
Yeah.
All
right. And I have no idea what a 4-dimensional tree would look like.
So that brings us to Klein bottles, which exist in the 4th dimension. And if you'll remember, the Mobius strip is one-sided, making it seem like it is 2-dimensional, but it can only exist in our 3-dimensional world. A Klein bottle is 3-dimensional that only exists in a 4-dimensional world. Kind of trippy. So this is another one-sided structure, and if you look at the shape of this Klein bottle, it's similar to that of a Mobius strip, and when cut in 2 properly, you have 2 Mobius strips. But this Klein bottle doesn't have any volume, despite the fact that it's a closed shape. And the reason a Klein bottle can't exist in our 3D world is because it has to make a hole through itself. It has to go through itself without creating a hole, which doesn't make sense, and that's why it's impossible in our world.
Okay. So now this brings us to something really weird. And it's a paradox in geometry that says that if matter can be infinitely decomposed, meaning if you can take a ball, decompose it into an infinite number of pieces, that you can rearrange those pieces, rotate them, reassemble them, and then end up with one more than what you started with. In our actual world, we can't infinitely decompose matter. There's actually a limit of how small things can get called the Planck length. It's actually been theorized that the reason that exists is because matter can be duplicated if that were the case. So
Now it's not.
what is a sphere? A sphere is a set of points. It is not a physical thing that you can hold, despite what we just told you. We kind of lied. It's actually a collection of points along the surface that are equidistant from the center. So each point on a sphere can be described in terms of coordinates as an angle. So think of latitude and longitude on the Earth. We describe where we are with two angles.
And the reason we say that a sphere is not a physical thing is because by definition, a sphere is where all points along the sphere are equidistant from the center. And this means that a sphere is made up of an infinite set of points. It's impossible to have a physical thing that's made up of infinite things. So that brings us more to this.
So kind of like I just said, each point on a circle, similar to a sphere, but we're just doing a cross section just because it's easier to animate.
Kind of like our trees.
Yes. Each red dot is marked as the angle increases by arc cosine of 1/3, which is a weird number, but it's irrational and it doesn't repeat when you go around an infinite number of times. You can touch every point on the circle surface except for the starting points. And eventually you will be left with a circle.
As you can kind of see here. And it's starting over.
So any point on that circle, almost any point except for the starting points, can be referenced in terms of how many rotations of that weird number you have to make in order to get there. So now this gets us to something weirder. A set, which is a word I've used before, is basically a collection of things. So for example, if you had a free group that contains some number of sets. So it contains sets SA, SB, and then their inverses, SA inverse and SB inverse.
And A inverse is the opposite of A, just like -1 is the opposite of 1. So when you put them next to each other, as you see here, you end up with nothing. -1 + 1 = 0. So something like this, negative B inverse B, BAA, BA inverse A, those inverses that are next to each other undo each other, and you're left with just BAAB. And the same thing happens down here.
So now this is where it gets complicated, but bear with me. This is S of A. This is a diagram of the first 3 iterations of S of A. So first, you can start with A. S of A is everything beginning with A. You
Any
can
sequence.
Yes, you can begin with A. Then you can have AA, you can have AB, or you can have B inverse. But of course, you can't have A inverse because then it would undo itself.
It's just 0.
And then next you have AAA, AAB, AAB inverse, and so on. But something interesting happens when we add A inverse to the start of all of these. So I'll do that over here. You add A inverse A inverse AA, A inverse AAA, and so on for all of these.
And as we discussed before, when you put these inverses next to each other, they end up as 0.
So as you can see, they undo each other.
And you end up with something a little bit like
this. So you get nothing in the beginning, and then you get 3 separate groups over here. But what's really cool is this group over here is actually exactly the same as S of A. So simply, literally just by adding A inverse to the beginning, by doing one thing, you've created S of A, and then you've also created S of B, and you've also created S of B inverse. So you've turned one set into 3 just by undoing one action.
Multiplied it by 3 infinities.
So as you can see, this over here is the same as that, as the original thing you started with. So this, again, gets a little messy, but you map each of those points to a sphere as a rotation. So A can be described as a rotation in one direction, A inverse as a rotation in the other direction. And then for B, it would simply be in the other plane, in another dimension, in the 3rd dimension that you can travel in our world. So if you map out all of those points, oops, it's the wrong one. If you map out all of those points, then what you can do is describe every point on the sphere as some combination of A inverse, B, and B inverse. And if you decompose them, rotate them the other way, and reassemble them, then kind of what I just showed here before, you can duplicate them.
Which is why you should, theoretically, be able to take an object, decompose it into these sets and then recreate it, so ending up with an original and a copy.
So something I mentioned before is that the starting points can't actually be duplicated, like over here. Where is it? Over here. So for example, the point exactly opposite of the starting point will never be reached. The point exactly vertical will never be reached, and the point exactly below will never be reached, just because eventually you'd be able to get to those points and get back to the starting point if that were the case. So any point that can be used as a starting point, we can't really describe in terms of a rotation of arc cosine of 1/3, which gets us back over here to the axiom of choice, which basically says that we can do that. We don't know why, but you can. And no explanation. It's just a rule, and you can. So a lot of mathematicians have rejected this paradox because of the axiom of choice, which basically just says you can duplicate these points, deal with it. Yeah, but you can still duplicate the set without the sphere and without the starting points. You can still duplicate a set simply by undoing one of the actions. So maybe it is still valid. We don't know. You want clicker?
Oh, thank you. I got the clicker. Okay, so so that is kind of a lot, but really, even if you didn't understand all of that, just like Jamie mentioned before, the point of this is just to show you how much we really doesn't make sense in our world. There are all of these things that theoretically should be true and obviously aren't. And there are some reasons for that, but we don't have all of the answers, but we're continuing to try to find them, hopefully. And sorry, go ahead.
I wasn't gonna say anything.
I lost my train of thought. But the reason that some of these things don't actually work is because, like we mentioned before, with the sphere, you can't have something made up of infinite things, because infinity is such a hard thing for us to comprehend, just like the fourth dimension is such a hard thing for us to comprehend. So when you put it out in numbers like this, it might make sense, but when you try to put it into the real world, it doesn't work.
And a lot of times there are rules that seemingly don't make sense, like why things can only be decomposed to a certain size, but actually in some connection to what Nate just said, there are some laws in the universe that, I don't know, maybe could exist to prevent things like Banach-Tarski from happening. So there are things that we still don't understand.
Thank you.
Yeah.
Sorry.
Hi, everybody. My name is John, and I am your friendly neighborhood econ teacher. It's my pleasure to introduce two of MA's amazing seniors, Kirsten Wang and Lexi Strack. They are taking a pretty big gamble with this presentation. They're going to try to make all of you better poker players, and I just bet that they will. I think there's a high probability that both Frank and I are better poker players for the time we spent with Lexi and Kirsten. So Lexi and Kirsten, shuffle up and deal.
Alrighty.
We need our
So,
clicker.
have you ever been sitting at a poker table and wondered, why does everyone have more chips than me?
Or have you never played poker before and want to learn how?
Maybe you have some high aspirations of winning the World Series of Poker.
Then you're in the right place. Today, we're going to be talking about the probability of Texas Hold'em. In our pre-calculus class junior year, we learned a little bit about the probability of 5-card poker, but we wanted to take that to the next level, looking at 7-card poker, where 2 cards you don't know, and so on. So it gets a lot more complicated.
Okay, so to start, we're going to go over the rules and vocab of Texas Hold'em for anyone who may not be familiar. So to start, each player is dealt 2 cards, and these are private. Only the person who has these 2 cards knows what they are. And then we have the first round of betting. So if you have 2 cards that you don't think are going to take you far, you might fold. Or if you feel faithful in your 2 cards, you might bet. So then we have the flop. And this is the first 3 cards, which are in the communal deck of cards that everyone can draw from and use to create their own 5-card hand. And so then after the flop, we have our next round of betting.
Then we have the turn, which is the 4th card in this communal pot. And then we have another round of betting. And then lastly, we have the river, which is the last and final card in our communal pot. And then once this card is flipped, each player knows which hand or what best hand they have. And so we have the final round of betting. And then if everyone is still in, they will reveal their cards and see who the winner is. So, and then in terms of general poker hand ratings, they go from the weakest, which is just a high card, to a royal flush, which is extremely rare. And each 5-card hand is assigned a value based on the probability of getting it. And so in a normal 5-card hand, they would range from most likely to least likely. But in the case of Texas Hold'em, it's slightly different just for a high card and a pair because since you have 7 cards, you're actually more likely to get a pair than to get a high card. But then as you can see, for each hand, it gets less and less likely the higher value the hand has.
So now we're going to look at specifically how this 4 of a kind percentage is calculated. And so there's something called the blank choose blank. And so in this way, your N, for example, which is the total number of objects in the set, which is the total number of cards that have, I think, the certain value. There's 13 different values in the deck. And then you need one of those values, which is going to be your one of a kind. And so then that's going to be your R, which is the number of chosen objects from that set. So then that gives you your first card. And then you have to multiply it by the other 3 cards that you want to do. So you know that when you take, then you're going to be left with 48 cards. And then you need the other 3 to get your 4 of a kind. And when you multiply those together using that complicated formula, you will end up with 0.168%.
Okay, so now we're going to test your guys' poker skills. So we're going to do a unrealistic simulation where you know that your opponent has pocket aces, which some of you might not know is a really good thing to have. And you have these 4 options: an ace king, 7-2, 2-3, and the 2-6. So we want you guys to turn and talk to the person next to you about which pair of cards you would want to have against this ace-ace. Okay, so so we go one by one. Should we just like go alternate everyone?
Yeah.
Okay.
And make sure if Heidi raised her hand, call on her. What? We're going to, because we got to give her like.
Wait, what do we do? What do we do? Okay, what do we do if no one takes it?
Then we call on one of them.
Wait, but if no one takes it, yeah.
Then it's fine.
Okay. We're gonna say what the percentages.
Yeah. I'm still gonna.
What are you guys thinking? Hard question, right? We're making you better in the case that you might have to play. All right, let's bring it back together. Oh wait,
Okay. Yeah,
which
that's
one's
right.
first? Okay, so did anyone choose the 3-2? Raise your hand. All right, would anyone like to share why they chose the 3-2? Yes, Luca.
You're kind of close to getting it straight.
Oh, yeah,
Okay,
2 cards
okay.
that like go next to each other are very appealing. So, sorry. All right. So the percentage of winning with a 3-2 against the ace-ace is 11.75%. So you're not in too bad a shape, but obviously you're not in great shape.
No. Okay. Did anyone pick the 2 and the 7? Ooh, okay. Okay.
Why did no one pick the 2 and the 7?
Why didn't you pick the 2 and the 7? Okay. Worst hand in poker?
Oh, Ellie, yes. Great.
Yeah.
Great thinking, Ellie.
Yeah.
That is correct.
Great thinking. Well, you're right.
Yes.
It is a pretty low percent, but it's awfully close to the 2 and the 3.
Yeah.
So that is because, or actually, we'll talk about that after we reveal the rest. Okay. Who picked?
Oh, who picked the 2 and the 6? Oh. Would anyone like to share why they picked the 2 and the 6?
Okay, okay.
Okay.
6 is better than 2 and 7 because you can get 3, 4, 5s, and either 1, 6, 1 or 7.
Exactly.
Yeah.
We have a poker professional in the crowd.
Yeah.
But yes, compared to the 2 and the 3 and the 2 and the 7, the 2 and the 6 has a higher chance of winning because you have more straight combinations because they range all the way from 1 to 10, whereas the 2 and the 3 only range from 1 to 6, and the 2 and the 7, well, you would need 4 cards,
4 of the cards
in the communal pot to get a straight.
All right.
Lastly, who chose the ace
So
and
who
the king?
chose the ace and the king? Okay, okay.
Would anyone like to share with us why they chose the ace and the king?
Okay, okay.
Okay.
So,
Well,
it's
you might
the
be
least
shocked,
likely.
but the ace and the king is actually the least likely pair to win against the ace and the ace.
It's about 50% less than all the other ones. I mean, obviously, in a real life simulation, if you had an ace and the king, you would not think to fold to begin with. But compared to an ace and an ace, you're not having great odds.
Yeah, and we're going to get into why in a second.
So, yeah. Okay. So now we're going to do a little practice simulation with the ace, and the ace king. So, looking here, if we go from the straight beginning, it's a little bit different probabilities, but it's just because there's a higher percentage of a tie. But that's your base probability. Now, if these are the cards played on the flop, which one are you guys staying in, or are you guys folding your ace king? Turn and talk.
Wait, are we doing this like they know that? Are we doing this like they know that they're up against an ace or like they don't?
They know.
Are you staying in, Victor? Wait. Wait, do they win this one? Do they win this time? Oh, yeah. Okay.
All right.
Okay. Does anyone want to take a stab at what they think the probability of winning with an ace king is right now? Oh, Heidi.
So we think that having so we know you have 3 of a kind, right? 3 aces.
Yeah, sure. We'll say we're the ace ace.
We have 2 of a kind, and we could get a royal flush, which so could you, but we were thinking. Right?
Mm-hmm. No, that's good. Good. Okay.
Yeah, okay.
Unfortunately, you have very low odds of actually winning. It is less than 1%.
Yeah. So if anyone said they would stay in on the ace king,
it's not looking too promising.
Rethink your choices. But obviously, if you had an ace king and this is the flop and you didn't know you're up against an ace ace, my bets are you're staying in because a 2 pair of ace and kings is pretty good. So we're going to keep rolling this out.
Okay. Now king's played.
Ooh.
What are you doing now?
What are you doing now?
Staying in, going out.
Turn and talk to your partner. Wait, what is the percentage on this one?
I think it's like, it's either like, I think it's 2%.
2%. Okay, so what's the tie percentage though?
I think it's kind of high. I think it's like 100% maybe. Couldn't say for sure.
All right. So, does anyone want to share what they are doing and why? Yeah.
Yeah.
Go for it. Oh, 2.
because it looks like, if I didn't know they had aces, I would stay in because that's crazy good hand. But knowing that they have two aces, I would fold because if we both have a full house, they have 3 aces and 2 kings, and I have 3 kings and 2 aces, and an ace is better than a king.
Right. Does anyone know the only possible card that could be flipped for the ace king to win? Yep. And what are the odds of that happening? 2.27% to be exact.
2.27%. And we'll talk about how that's calculated in the next simulation. But yeah, so in our simulation, 7's played. Shucks, you don't win. Another one. This one is going to be between the ace and the ace and the 2 and the 6. So here's your base percentages. You're looking a little better than the ace and the king, but not great. So here's the flop. Are you staying in? Are you going out? Turn
and talk. Okay, so this one, the only way they could win is if it's a straight, right?
Straight, yeah.
And then
they need 1 card.
Yeah, pair, triple. They have their cheat sheet.
How do they know?
And they have trip aces.
Okay. Who said they would like to stay in with the 2 and 6?
Okay.
Who said they would want to fold in 2 and 6? Oh. Seems pretty even.
Okay.
All right. So the probability of the 2 and 6 winning actually goes, did that go up? Yeah. Actually goes up to 15.35%. Does anyone know why? Yeah, Luca? Exactly. So that probability right here is the probability of getting a 3 in either of these 2 cards in order to complete the straight. But obviously, if you have a pair of aces and there's an ace in the flop, you're feeling pretty confident right now.
Okay. Next, queen is played. So we're going to zoom in and look at how this 9% is calculated. Because, as you saw, your odds went down. And what's the 1 card that we need to win? Does anyone know? Yes. Okay. So how is this calculated? It's actually quite simple. But basically, it's the possible outcomes over the total number of cards. So as you can see up there, there's 4 threes still in the deck. And there's 52 cards in the deck. 8 have already been flipped. 52 minus 8, 44. 4 divided by 44, 0.9. And yeah, so we have it that you guys win. So if you guys stayed in with 2 and 6, then you won. So good job.
So even though the odds might not be telling you to stay in, if you're more of a risky poker player and you feel like confident that your luck is good today, then you can stay in and possibly win that.
Yeah. So
all right.
Thank you.
Well, I'm just going to make a couple of quick closing comments, and then we can be on our way. But thank you all so much. First things, I'm actually going to thank Travis and the admin team. I really appreciate you guys always giving us the opportunity to put this on and doing what we want to do and taking the time to really work with everybody. Funny story is we had this date we had math night actually to be on Thursday or another day. And Travis couldn't make it, and because she's such a math enthusiast, and made famous by Kaylin and Drayson, we made sure that she was going to be able to make it today. Huge thank you to all the families, siblings, everything like that for your support of the students and the presenters today. Another huge thank you to and the communications team, Melissa, for everything you've done, Justine and Julie for sending everything out. Our musical performance in the beginning, it was Alex Hayward, Nate, Jonah, and Matthew. Am I missing anybody? I think that's good. One more thank you to the math department for, again, all of their support for the students. I'll go down the list just in case everybody forgot who they were. Ian, Molly, Anya, Taylor, Rachel, Josh, Kevin, Jamie, and John.
And Frank.
Oh, and me, yeah, okay. And then this one I'm going to make sure I get right. And one more huge thank you to all the presenters. We have Charlie, Victor, Nate, Kaylin, Drayson, Eugene, Gordon, Tilly, Luca, Lexi, and Kirsten. One more big round of applause. If I can have all the presenters come on up here. We have math department has a little gift for you, and we want to have one big final picture, and then you're off, free to go.